By now, you've probably noticed that in this section, we're revisiting all the stuff we've already learned about vector spaces. Um, there, we were learning about vector spaces with real numbers in vectors, and that was pretty much all we had to deal with. But now that we know that vector spaces can be made up of different kinds of things, we need to revisit the properties we know about vector spaces of real numbers and make sure that they apply. And in fact, they do. So each sort of topic, each video starts with a little review of what it means to be a vector space, or, okay, the field one was new. That was new information. Um, Although the real numbers are a field, right? And we were working with the real numbers without explicitly stating that that was a restriction on the particular vector space we were using. So now what we're going to talk about is the basis of a vector space, but what I'm going to do is start by reviewing what it means to be the basis of a vector space in the real numbers. And here's the definition. This is sort of slightly paraphrased, but here's the definition we came up with in section 5.4, basis and dimension. A basis is just a subset of a vector space with some criteria attached to it. So you take a subset of a collection of vectors, and if that subset is linearly independent and it also spans the entire space, we called that a minimal spanning set as well. I think that was in section 5.3, linear independence and dependence. At the end of that section, we talked about minimal spanning sets. This is the same as a minimal spanning set. It's a spanning set, right? It's a subset of V that spans all of V. But also, it's the minimum number of vectors required to do that. So the example I like to give here, the sort of most intuitive example, is that if you have 10 vectors in R3, if our vector space is R3, and you have 10 vectors in R3, there's a very good chance that will span R3. There's no guarantee unless they're also linearly independent. Well, 10 vectors in R3 cannot be linearly independent because the number of vectors you need, the minimal number of vectors you need to span R3 is 3, because you can make up any other vector in R3 from a linear combination of those 3 linearly independent vectors. So picturing R3 and 3 vectors in R3 all going off in different directions, linearly independent vectors, you have the minimum number of vectors required to span R3, and that's called a minimal spanning set. It's also called a basis, right? So the word basis is really just another way of saying minimal spanning set. So that's how we defined a basis in the Euclidean vector spaces that we were working with. But the same definition applies here with one small modification. And that is, we would say S is a subset of V. If S is a subset of V, it's a basis of V over a field F. And that's the only adjustment we need to make. All we're doing here is, when we were in Euclidean vector spaces, we assumed that we were working with real numbers. So we assumed that our field was R, all real numbers, and so we didn't state it. We assumed that because it's comfortable, it's familiar to us. Now we're getting into a place in this course content, where we know that we're not restricted just to the real numbers. We can use any field we like now that we know what a field is. If we don't know what the field is, or if it's not stated, if we know we're in some other vector space other than vectors in Rn, then we can assume that the field that we're working with is the same as the superspace, right? The superset, the vector space we're living in. So if this is R3, we will say that the subset is a basis of R3 over R3. So there's a little redundancy there, but it also means that you've captured the entire vector space that you're working with. You haven't left anything out, but you haven't gone beyond it either. An ordered basis is just one in which the vectors in the basis have to be in a particular order. We're not going to worry about that in this course. There's a section in the textbook called coordinatization that I'm leaving in the textbook, this is a textbook that I can take sections out of, or I can move them around. I'm going to leave that section in the textbook in case you're interested in looking at it. But I'm marking it as optional. So it should be obvious that you don't need to do the content in that section. But that is at least one of the places where you might see coordinates, or where you might see a need for an ordered basis. We're not going to worry about ordered bases in the rest of this quarter. There are a couple of examples, or are they examples or questions? There's one example and one participation activity that ask you to determine whether a set of vectors is a basis for the space that they're talking about. One is a set of polynomial vectors, and one is a set of matrix vectors. One is a set of matrices, 2x2 matrices. I'm going to leave those to you to read through and try, because I think they're fairly straightforward. But I would like to talk about an example here. And so I want to start with a couple of reminders. One is that we need to remember that a vector space has four things associated with it. One is the set of vectors. One is a set of scalars. And the last two are two binary operations. Or you might say operators. I'll say operations here. And usually those are addition and scalar multiplication. So we need those four things to be talking about a vector space to begin with. In the example I have up here, it's not really an example, but the definition I have up here for basis, V is the set of vectors. That's my vectors. The set of scalars is my field. So that might be R, or it might be V itself, depending on the context or how much information you're given. And the two binary operators are addition and scalar multiplication. So we need those four things. And remember that this is what we're calling a field. It is a field. That's where we get our scalars. So that's one reminder. The other is that a basis can be reduced to a point where we call it a standard basis. So for example, the standard basis for, let's see here. If I'm in R2, then a vector in R2 looks something like this, right? AB. And if I want to create a basis for this, then one way to do it is to take two vectors. I need two because I'm in R2. And think of how they would look in a matrix as a row-reduced matrix. I'd have these two vectors, right? I'd have those two columns in a matrix if it was row-reduced all the way down to reduced echelon form. So those are this collection of vectors. I'll call B for basis. That's a basis for R2. Those two vectors are linearly independent and they span R2. So they are a basis. Not only that, because they're sort of the most sort of simplified basis in R2, we call it a standard basis. So I'm going to be talking now about standard bases. Standard bases. Okay. Let me erase this. That was just an example. So those are the things I wanted to remind you of. what I'm going to do now is I'm going to talk about an example of a basis a basis of a vector space that we haven't talked about yet so far, and that is the complex numbers. So I'm going to take the wrong color of pen. Let's change that. I'm going to take the complex numbers. I'm going to notate C2, and I'm going to, so that's my vector space. Let me write V equals that. V equals C2, so that you know that that's my vector space. And I'm going to define this as being equal to any two elements from a set of numbers that looks like this, a plus bi, where a and b are both real numbers. So this is from algebra, right? A plus bi is a complex number. A and b are real numbers, but a is the real part, and bi is the imaginary part of that complex number. So a and b are real, but this number here is a complex number with an imaginary part. And to be a member of the set C, you have to take two of these. So I'm going to call one element of this set little c, and I'm going to say that it looks like this. Let's go a plus bi together with c plus, I shouldn't use that c there, should I? Let's use k plus di. Okay, so I have two complex numbers, and maybe I'll put these in brackets, and that is what makes up one element of the set C2. Now I haven't specified a field here, so I'm going to do that now over the complex numbers. So C2 is my vector field. The complex numbers is my vector space. The complex numbers is my field. So this is where I'm going to take my scalars from. So when I write a standard basis for this vector space, I can write it like this. Let's call it S, and it's a set, it's a collection of vectors. So I'll write my two vectors, and then I'll fill them in. And they are 1, 0, 0, 1. It's not the only basis. It's not the only possible combination of linearly independent vectors that span C2, but it's the most sort of simplified one, right? It's the standard one. The reason this is a standard basis for C2 over the complex numbers is that because I have the complex numbers as my scalars, right? This is my field that I'm drawing from. I can take both real numbers and complex numbers as scalars here. So if I took m times 1, 0 plus n times 0, 1, that would be a linear combination. M and n can be I, or 0, or -3, or pi, and so can n. N could be I, or 1, or 0, or e, right? These are my scalars. So these are drawn from the complex numbers because that's the field I've been given to work with. And that means the numbers that I can pull from are any complex number, not just any real number. Okay? So I could also use 3i plus 2 here as a scalar. So I can write a linear combination of these two vectors using more than just the real numbers as scalars. So that makes this a basis for a standard basis for C2 over the complex numbers with this field. All right, now I'm going to do another one. Let's see if I can squeeze it in here. Actually, I'm just going to do it by changing color because it's really quite interesting what happens here. If I restrict my field to R, then my standard basis needs to be I'm going to run out of room. I know you're shocked. Let me do it this way. I'll get a little creative with how I arrange this. S equals, put them vertically like this. This time I'm going to need 4 because I need to have complex numbers in my element, but I can't draw from the complex numbers to scale, right? So I have to find a different way to make sure I can include combinations that have complex numbers in them. So I'm going to have 1, 0, and 0, 1, but I'm also going to have I, 0, and 0, I. That is a standard basis for C2 under the real numbers, under the field of the, or over the field of the real numbers. You see the difference. So what field we're working with is actually very important. It changes what the basis, or what a basis might be, that will both span the vector space and be linearly independent. So this example is a bit beyond what I'm going to ask of you, but I wanted you to see it because I wanted you to see what the difference was by using a different field.